day 4 video, and it's really definition heavy about walks and paths and circuits and Euler circuits, just what it means. So let's just start off with a previous example. Here's an edge endpoint function, so we should be able to draw a graph. Looks like we have 5 vertices, so v1, v2, and v5. And then we'll see what happens. Edge 1 just goes from v1, so it must be just a loop. Edge 2 is from 2 to 4, so we got them right there. 3 to 5 is another one. And 1 to 3 is edge 4. Okay, so that's kind of our graph. There are some implications about this. It's something that's it's not connected, but we'll get to that. So I'm not worried about that right now. This is a good indication. All right, so let's say we got some vertices. Edge 1 is up there. Edge 2 is another bubble. Looks like edge 3 and 4 are going to be doing the same things. That's edge 3, and this is edge 4. And then edge 5 is what's a loop that's on 3. Anyway, so a walk would constitute as a walk is just any alternating sequence of adjacent edges and vertices. So, I mean, we could say, let's say we started at V1. We could start anywhere, but let's say a walk would be, V1. So we started at V1, we did edge 1, now we're at V2. Then maybe we went to V3 via edge 4. We're at V3 now, and we did edge 5, and then maybe we took, so we're still at V3 now. Maybe we then went back to V2 from edge 3, and let's say we stopped there. Let's worry, that's our walk. Kind of ambling a little bit, but we went, here, and then 4, did the loop, took the E3 back, and stayed there. It's a walk. Path is the same thing as a walk, but all edges are distinct, except possibly the first and last. In other words, there should be no repeating edges. So this last sentence is kind of messed up. Or the last parentheses. They should all be distinct. So if we did a walk, or if we did a path, we could say that maybe we wanted to get to the V3 and back. I'm only going to list the edges. So from V1 and to V3, we would go E1, E3, because now we're down to V3, and we want to go. So that's a path, and we just didn't, they're distinct edges. We didn't repeat anything, and we didn't have to go all the way back to the beginning. But I'm gonna, just for fun, we go E4 then from there, and then E2. So we made it from V1 to V3 and back without repeating any edges. So that's a path. I could have also just said, hey, I'm going from V1 to V2, and I want a path. All right, E1, done. So there's no specific length or anything. And you don't have to go anywhere or start any specific place unless indicated. Then, a circuit is actually what I just did. It's a path that ends at the same vertex as it began. So, and the circuit is a path. So we're not supposed to repeat any edges. So we could just say that was exactly what we just did. That was E1 to E3, E4, and E2. We got back to V1, and we started at V1. So that would have been an example of a circuit. And it's a path, so your edges got to be distinct. An Euler circuit is a circuit. So this is kind of like the Russian dolls thing. Like each definition is based off the previous definition. So in an Euler circuit, well, if it's a circle, it's also a path. And that means that it's a path, it's a walk, but it has to have distinct edges. No repeats. And an Euler circuit, so since it's a circuit, it not only is a path that has distinct edges, it also starts and stops at the same vertex. And then an Euler circuit, it uses every edge and vertex once. So we could have made an Euler circuit right here, except we would have then used V2 twice, and we would use V3 a couple times, and we wouldn't have done the loop, so we would have missed out on the Euler circuit. But that's the main thing. Euler circuits are hard to come by because you have to use every edge and vertex once. Okay, so here's another example. This is actually this exact same thing I drew before. A walk could be anything we just did. A path, E1 to E3. And we just stopped there, We could also do a loop at V5 or E5, but we repeated a vertex then, which is okay sometimes for a path. It's usually talking about distinct edges. Excuse me. So a circuit then could just be from E1 to E2, because then you start and stop at the same spot, and you use distinct edges, like a path. You didn't repeat edges. In an Euler circuit here, you could say that we go from E1, E3, E5. So now maybe I'll do this in blue. So E1, E3, E5, and then we go E4 back to this, and then back to E1. So we hit every edge once, and we started and stopped at the same spot. We did repeat vertices, but typically we only care about the edges being traversed, not the vertices. Like vertices are okay to repeat, in other words, but edges are not if there's a stipulation like an Euler circuit or a path. So this one, we listed out what it was. Start and stop at the same spot, hit all edges once. Here's another graph. Give a walk from V1 to V4. So this is easy. We'll just take edge. We'll just take edge 2, edge 3, and then edge 5, and we did it. You have a path from V1 to V4. Well, that's the same thing. I mean, this would be the exact same thing. I just did a path. I could have elected from a walk to be like E2, E3, E4, E3, E3, E5. That would be a walk because, walk can be whatever. For the path, you have to have distinct edges. So we already did that. Give a circuit on the graph. So we just got to start and stop at the same spot, and only use any edge once. So it's not an Euler circuit yet, just a circuit. So we could say if we started V1, we could go E2, E3, E6, and then E8, because what that did was 2, 3, 6, 8. We got back to V1 where we chose to start. And is this an Euler circuit? We can tell. There is an easy way to tell right away. There's no way for us to get to V4 at any point without traveling E5 twice. So no matter where you start, if you start at V2 or whatever, you've started V3, in order to even get this edge 5, either you hit it at the end, but then you didn't make it back to where you started, so it's not a circuit. Or you started with V4, do some other stuff, but then when you have to come back to it, you're gonna have to travel E5 again. So it's not an Euler circuit. You can't make an Euler circuit with this graph. And there's a corollary for that, or a theorem. It says if a graph has an Euler circuit, then every vertex of the graph has even degree. And we can tell right now, some of these vertices do not have even degree. Like V2 right here has degree 3, so already it's not going to work. So one last thing, I think, is if something is connected. So a graph has to be connected if it's possible to travel from any vertex to any other vertex through adjacent edges. It just means, can you get, starting at any point, can you get to all points? And it just has to be through a walk. It doesn't have to be a path or a circuit or anything. So I see right here that there's no way I can get to 4. There's no edge that connects to it. So simply, no, it's not connected. This guy, if I start at V1, I can go V2, I can go that edge, here, here. I can go to 4, and I've hit all of the vertices. So yes. This guy, at first it can look connected because they all at least have edges connecting them. But if I start at V1, I don't have an option to get to V4 or V5. This isn't like an intersection like we used to think of with intersecting lines and stuff like that. These are like it's not a connected graph because this portion right there can't get to any of the vertices through an edge, through a common edge. So no, it's not connected. And then there's another thing about Euler circuits. So do these following graphs have an Euler circuit? If so, find it. If not, why not? And so we already kind of know something about it, and so the theorem is right down there. But you could try it out. So if I start here, 1, 2, 3, I could go back to the center right there, but then I did a circuit, but I missed this thing, so this was not an Euler circuit. Ultimately, that's degree 3. So is that. So I kind of know that it's not going to be. We could try this guy. You could try it out for a little while, see if you can make it work. Nope. I started up here, and I didn't get everywhere. And we should also know that if it's an Euler circuit, then every vertex of the graph has an even degree. And that's not true. This has degree 3 right there. So it's over. This guy you can make work. If you look at each vertex, the conditions are there. They all have degree 4. So I could travel it, and I would say, maybe I go here. I might mess this up the first time. I'm not sure. Here, here, here. Oh yeah, I messed up. Then if I go here, I need to go all the way back already. Oh yeah, I can do it. And then down, and then around. So if you play that back, I can probably just do that again too. So I don't know, it's not that bad. So I went right, down, we went up, down, maybe I went over here. So I'm doing it a little bit differently, but I'm doing it. Notice that I only hit every edge once. I hit vertices different times, but it's an Euler circuit because I started and stopped right here. I only hit every edge once, and every edge exactly once. So that's what makes it an Euler circuit. Specifically, another way of writing this is that if every vertex of a graph has even degree, then it has an Euler circuit. And then here's just another definition page if you wanna look at this instead of having to go back. But these are the definitions that we just used. Path, walk. Walks can be infinite as well, if I haven't stated that. There's an Euler circuit.